Okay, so in this last part of this section, what we're going to do is we're going to combine optimization with Newton's method, okay? And the optimization problem we're going to do is number 39, and number 39 is going to be dealing with the distance formula. So before we start, let's just take a trip down memory lane and go back to our distance formula between 2 points. All right, and then how we find the distance between two ordered pairs, we use the Pythagorean theorem, right? If this is the point x1, y1, and this is x2, y2. All right, we're going to look at the distance from x1 to x2. We're going to look at the distance between y1 and y2. Okay, so we want to find this distance. And we do it with the Pythagorean theorem. So we create this right triangle. Okay, so this is how we derived it in pre-calc and algebra. And then we know d squared is equal to a squared plus b squared. So if we just want to find d, we're going to take the square root of that sum. So here's side the base squared plus the height squared. Okay, so there's your distance formula, and we're going to use that in this next problem. We're looking at number 39. So number 39 says we're going to use Newton's method to find the coordinates correct to 6 decimal places of the point on the parabola y equals x minus 1 squared that is closest to the origin. All right, well, if we're talking about closest, what kind of problem are we in? We're in an optimization problem. Okay, so we want to find the point that's closest to the origin. So if you want to just draw a quick little sketch, let's see, x squared is a parabola, x minus 1 is a shift to the right 1 unit. I don't know what I'm doing. I'm just doing a sketch. I don't know why I'm getting so accurate. But anyway, it's going to look something like this. So here's our parabola. Quick little sketch by translation, translating that x squared. And they want to know, find the closest point on the parabola, the closest point to the origin. All right, so here's our origin, and then I'll just guess. I don't know what this point is. I'll just call it xy. And the closest point to the origin, it would be a straight line, so we're just going to call that D. And we want to optimize D. So remember, in our optimization section, we always write out what we want to optimize. We're going to optimize D, the square root of, x2 minus x1 squared. Okay. All right, so there you go. Let's start plugging things in. First of all, we have the point x and y. That's one point. And then what's the other point? 0, 0. That's just awesome. I love working with zeros, all right? So really, D is equal to the square root of, let's see, it's going to be x minus, so x2 minus x1. So x minus 0 is x. And then plus y minus 0, right? y2 minus y1. Y minus 0 is just y, so then it's y squared. So that looks better, okay? So this is what we want to optimize. And remember, in our optimization section, once we have the function we want to optimize, we have to get it into one variable, okay? And we do that using the other information. The other information is that this curve is y equals x minus 1 all squared. So we're going to make that substitution, right? We're going to plug in that y into our optimization function, that distance. So now it's the distance is equal to the square root of x squared plus y, which is x minus 1 squared, and then we're going to square it. So remember, y is that whole function. All right, so what we're optimizing is x squared, let's see, squared, 2 times 2 is 4. It's this. It's that monster. We're going to optimize that. That looks like a y, but that should be a 4. Okay. And it's always good to, you know, give an interval of values. And if you look at this, I would say we could safely say that x is going to be between 0 and 1. All right. All right, so there you go. All right, so, and notice the distance at x equals 0 and x equals 1. The distance from the origin is 1, right? This distance is 1 and that distance is 1, okay? So hopefully this distance somewhere between the points is less than 1. All right, so I'm just going to make that note. So here we go. So once we have what we're optimizing, we take the derivative, okay? So let's take the derivative. This is now a function of x, so I'll do d prime of x. We are going to use the chain rule. Okay, so there's the derivative of the outside function, then the derivative of the inside function. Okay, so just to kind of clean it up so we know, you know, where the undefined parts are, where the zeros are. This last thing we wrote is the only thing in the numerator. And the denominators are the 2, and then the square root of x squared plus x minus 1 to the 4th. Okay. So now that we have the derivative and we're trying to optimize, we have to find the critical numbers. So critical numbers, again, are where d prime is undefined and where d prime, the derivative, is 0. All right, so let's look at undefined first. Whoops. Undefined is when the denominator equals 0. It's supposed to be, I'm just going to rewrite that. Undefined is when the denominator equals 0. And the denominator is 0. Hold on, I don't have to write everything out. The denominator is 0 when the radicand is 0. So when x squared plus x minus 1 to the 4th is equal to 0. And not only that, let me take it one notch more. It's less than or equal to 0, because it also can't be negative, right? So if we were to solve that, look at this. So this would have to be that x squared, if we subtract that x minus 1 to the 4th, we would get this. Okay, so we have a positive number is equal to a negative positive number, right? Because x squared and x to the 4th are always positive. So when is a positive number less than a negative number? It can't happen, right? So the radicand is never less than 0. And then how about if it was just equal to 0? So x squared equal to x minus 1 to the 4th. All right, that's what would happen if it was equal to 0. And let's see, well, it could only happen if it at 0, right? If they're both equal to 0, and that can't happen, right? If one is 0, the other one is negative 4th as well. So this is no solution, okay? So we're going to rely on d prime of x equal to 0. So the derivative is equal to 0. And the derivative is equal to 0 when the numerator is equal to 0. Okay, so when the numerator is equal to 0, that means the whole derivative is 0. So here is our numerator. Make sure I'm writing it down correctly. All right, so we have this polynomial function. what can we do? Let's expand this. X minus 1 cubed. So you can do, x minus 1 times x minus 1, FOIL that out, and then do x minus 1 again. And you get x cubed minus 3x squared plus 3x minus 1. Okay, let's distribute that 4. Okay, now what can we do? There's a 2x plus 12x we could take care of. So we have 14x. All right, equals 0. We can factor out of 2, all right? Okay, so at this point in calculus, what we would do is we would try to factor this more, right? Because it's a cubic, right? If it was a quadratic, we could just use the quadratic formula. But let me just do a little thought bubble. In pre-calc, we figured out how to find potential rational zeros. Right, by looking at the multiples, the ratios of the multiples of the first and the last term. All right, so this is the rational zero theorem from calculus, right? And we would see if any of those zeros satisfied this equation, and we know the connection between zeros and factors, okay? So that's how we could factor it. But how could we find the irrational zeros, okay? And that's the situation we're in. So to find the irrational zeros, since we don't have the quadratic formula can find irrational zeros, but only for quadratic equations, right? So to find the irrational zeros in this case, we have to use Newton's method. All right, so that's how we're going to solve that equation. So what we're going to do is we're going to call that last factor f, and we're going to find solutions to it. We're going to find the zeros. And whatever the zeros are of this, those are going to be our critical numbers. Because remember, whatever solves that for the 0, let me just trace back what we're doing, that's going to be where the derivative is 0. That's where it came from. This is where, d prime of x is equal to 0. And that's going to give us our critical number. That's going to be the smallest distance. Okay, so let's remind ourselves of our formula. It's always helpful to look at the formula and see what we need. So we have our function. We're going to have to find the derivative, and we're going to have to find xn. All right, so I like to plug in, the whole function sometimes, especially if I'm using my graphing calculator. And then the derivative, let's see, is 6x squared. We can do this as we go, minus 12x plus 7. Okay, so we have to find x1. Okay, and then we can just stare at this. Sometimes we make a guess, sometimes it's number sense. I'm looking at the constant. The constant's -2. So if I plug in 0 to our polynomial, we're going to get that constant, -2. So I'm going to try a number close to 0. How about 1? And what happens if I plug in 1? We're going to get 2 minus 6 plus 7 minus 2 is equal to +1. All right, so there we go. So f of 0 is negative, and f of 1 is positive. So we know the 0 is between those. So that means there's a root between 0 and 1, okay, by the IVT. Okay, so now we know, you can choose either one. I'm just going to choose x of 1 equal to 1. Okay, so that means x of 2 in this formula I got upstairs is going to be 1 minus f of 1 in that big long formula and divided by f prime of 1. And if you're using a scientific calculator, you might have to plug it in each time. So doable on a scientific calculator for sure, but a graphing calculator is helpful. Okay, and if you plug all this in, you're going to get 0. Okay, so x of 2 is 0. All right, and then you're going to rinse, wash, and repeat. And remember, we want an accuracy of 3 or 6 decimals. So then x of 3, let me just write it out. It's going to be this. And you can verify this with your calculator. Just rinse, wash, and repeat. Very repetitive. .285714. X of 4. All right, so just 6 decimals because that's where we're going. And then x5, 9.6. Not a whole lot of consistency yet. We are getting closer to a number for sure. All right, and then notice when we finally hit x7, 0.410245. And I think up here I had 1 too many. Sorry about that. All right, there you go. And then look at, we have a little bit of stability, and we have 1, 2, 3, 4, 5, 6 decimals. So that is our way we're approximating where the derivative is approximately 0. We're saying d prime of that critical number, 2, 4, 5, is approximately 0. Okay, so that's the critical number. So that's the one that's minimizing the distance. Okay, and let's make sure we answer the question. We want the coordinates. So this is the x coordinate. So to find the y coordinate, y is again x minus 1 squared. So we would put in our 0, 2, 4, 5. We would subtract 1 and square it in our calculator to get our other coordinate. And there you go. So that's how we can combine our optimization problems using Newton's method.